So you need your own copy of the test. Average was about 50% on this. I've done this test before and I got 1 wrong. That's not bad, still got my 7. Okay. So homogeneous mixture. Well, according to the IB, a mixture contains one or more elements and or compounds that are not chemically bonded together and retain their individual properties. So that's going to exclude 1A, because oil and water don't mix. Now, a homogeneous mixture is something like a tea or vodka. Your first sip of tea, your last sip of tea from the cup, vodka from the top, middle, or the bottom of the bottle, it's homogeneous. It has the same composition from the mixture components. And so that's the actual answer. One is C. What's a heterogeneous mixture? Well, that's like something where you take samples and each sample has a different composition. So maybe taking bites out of a chocolate chip cookie. Maybe you'll have more chocolate chips or less sugar. It's not a very chemistry question. Thorny there, forget about it. It's still a good example. Vegetable soup as well. Okay, empirical formula. So do a big C and a big H because it's a hydrocarbon. I'm going to put a 12 there and a 1 there, the molar masses. And at the top, the percentage, or the mass if they gave it to me. That's going to be 100 minus 84.6, which is 15.4, 15.4. So I'm basically working out the moles of each one. So I can do that as hydrogen 15.4. That looks like a nasty number. And carbon, is that 7? About 7? Ugh. C7H15. I was hoping for C7H14, but you know what? I'm just going to say CH2 is the empirical formula. Close enough. Now the molecular formula, the molecular mass is going to be 142. So I'm going to divide that by 14. Now where does the 14 come from? Well, carbon's 12, hydrogen's 1. So that means the actual real molecule contains 10 lots of CH2. Because that gives you about 10. So that's going to be C10H20. That isn't any of the answers, but the closest is C. And that just feels weird, like I did some over-rounding, some under-rounding. Oh, but C's the answer. Or you could just look at molecules A, B, C, and D, and then just add up their molar masses and see which one's 142. That's the other way to do that. Question 3, ideal gas. Ideal gas graphs look like that, with one exception, which is the one the IB often asks about. One of the graphs looks like this. That's the pressure volume graph. Double the pressure, half the volume. And yeah, that's the one they're asking, volume and pressure. So 3 is A. 4. I like to use the boxes method. Even if you don't know what you're doing, you can still follow the boxes method rules, get the answer. Hopefully you do know what you're doing. So that's moles, mass, and molar mass. And there's a 7 in there, 7 grams of ethene. So I want to work out the moles, but ultimately I want to work out this. But to get there, I'm going to have to work out the moles of ethene. So the molar mass of ethene is 28. It's 12 and 12 from the 2 carbons, and then 4 from the 4 hydrogens. And so moles is mass over molar mass, so that's going to give me 7 over 28. And I'm going to keep the fractions because the answers are in fractions. So since 1 ethene makes 1 ethanol, 7/28 of ethene is going to make 7/28 of methanol. Now I need the mass. So mass is moles times molar mass. I know the moles, it's 7 over 28. And the molar mass of ethanol, well, let's work that out. Got 12 and 12 and 6 for the hydrogens and 16. 46. So that's 46. Excuse me, 46. So I'm going to multiply the moles by the molar mass over 46. Right, so that line's going to go there, isn't it? It's a bit messy. Let me rewrite that. 7 times 46 over 28. So that's the theoretical yield. T table, T theoretical. But it says experimentally I made 7 grams. Okay. Is it 7 grams? No, 6 grams, excuse me, 6 grams. So experimental over theoretical times 100. That's going to be my yield. So I'm going to multiply that by 100. Now that looks pretty ugly. There's no way that's going to be one of the answers. So how can I fix that algebraically? This 28, I can move it up to the top there and make it multiply by 28. So I can erase that 28 from the bottom and that nasty line. So what's that? 6, 28, 100. So that's D. 4 is D. That took me more than a minute and a half, which is the allocated time for these questions. Easiest question, 89% got it correct. Least discriminating. You're good at this, you're bad at this, everyone got this. Protons, neutrons, and electrons. Well, first of all, let me go up to the periodic table, look for phosphorus, and I can see that has 15 for atomic number. So that means it has 15 protons. So protons is 15. The difference between these numbers is the neutrons. So that's going to be 16. And the electrons, well, it looks like the electrons is also going to be 15. But don't forget to include those 3. So I'm going to add 3. It's going to give me 18. Which is A. So 5 is A. 6. Emission spectra. So I remember Roy G. Biv. Ultraviolet, ultraviolet. So the kind of UV is here. So this is the high energy. Ultraviolet, ultraviolet. Red has a lower energy than blue. Yeah. If this is the high energy, and this ends the low energy, red does have a lower energy than blue. So I is correct. Is that enough? It just tells me that C is wrong. Let's look at the second one. Lines converge at longer wavelength. You just have to remember, lines converge at high frequency. Lines converge at high frequency. Just remember that. So high frequency, that's high frequency, so that's going to have a short wavelength. So 2's wrong. If 2's wrong, A must be wrong, D must be wrong. So it's B. 6 is B. Yep, 6B. 7, the most discriminating. So only the higher scoring students got this right. Sodium oxide, Na2O. Well, I can see it's made of a metal, sodium, and a non-metal. Metals hate electrons, so electrons must have gone from the metal to the non-metal, 2 of them actually, making ions. So that's ionic bonding. So it has to be C or D for ionic bonding. Now, sodium oxide is an alkali metal, and alkali metals make alkali solutions in water. So alkali solution is above 7, so it's high. So 7 is going to be D. Let's just look at the conductivity, the middle column there. Conductivity. So for anything to conduct electricity, you need freely moving charged particles. Now, sodium oxide's ionic, and ionic crystals are solid. So if they're solid, although they have ions, they do have charged particles. If it's a solid, and all ionic crystals are solid, it's a strong bond, they're not freely moving, they're locked into that lattice. Well, how could I unlock them from that lattice? Well, you could melt it or dissolve it in water. Dissolving in water is high level, so you could just melt it, turn it into a liquid. So yeah, ionic substances conduct as a liquid, because then you've made the charged particles freely moving. Question 8. Which statement's correct? Periodic table. I see atomic radius there. So I think Fat Frank, he's the biggest one there. Francium, down in the corner. Fat Frank. So going down a group, radius increases, and going across a group, radius must decrease, because Frank is the fattest. So 8a, atomic radius decreases down group 17. No, that's not right. As you go down a group, they get bigger. So A is wrong. Let's look at C. Atomic radius increases across. No, it doesn't get bigger as you go across. It gets smaller, because Frank's the biggest. So it isn't atomic radius. It must be ionization energy. So ionization energy is how easy it is to pull an electron off of an atom. Actually, francium has the lowest first ionization energy. It's really easy, which means it requires a very small amount of energy to rip an electron off of a francium atom. Why is that? Francium's enormous. The distance between the electron and the nucleus is huge. The electron's far from the pull of the nucleus. And also there's lots of shielding electrons there in between. So francium has the lowest first ionization energy. So that's B, 8b. As you go down a group, it's easier to pull off the electron, because the electron's further from the pull of the nucleus. Ammonium phosphate, so you need to remember 9 ions. For IB, you need hydroxide, you need hydrogen carbonate, you need carbonate, you need sulfate, you need phosphate. 1, 2, 3, 4, 5. You need ammonium. You need nitrate. 1, 2, 3, 4, 5, 6, 7. There. That's the 7 you need. So ammonium is NH4+, and phosphate is PO4 3-. Use the crisscross rule. So that's going to be a 1 goes here, and a 3 goes there. What the hell does that mean? Well, I've got ammonium, and I've got phosphate. So the 3 goes here, and the 1 goes there. 9b. 10, the easiest question. Second easiest question. What doesn't conduct electricity very well? Okay, I can see the answer is diamond. That's the worst conductor. So what is it about graphite, graphene, and carbon nanotubes? Well, anything with freely moving charged particles can conduct electricity. So all of them have electrons that are not locked in a bond. So graphite, graphene, and carbon nanotubes, the carbon atoms have 3 bonds, covalent bonds to their neighbours, and those electrons are not freely moving. But where you'd expect a 4th bond, carbon normally has 4th bond, that electron is just running around free. In diamond, the carbon in diamond, each carbon in diamond, the valence electrons are bonded to other carbons, so they're not free to run around. So that's 10. 11, the nitrate ion. I would advise you learn how to draw this without doing it from first principles, but let's do it from first principles. Nitrogen's in group 15, oxygen's in group 16, and an extra electron there. So that's how many valence electrons there are. 24. I'm interested in pairs of valence electrons, so I'm going to divide by 2. That gives me 12 pairs of electrons. Nitrogen goes in the center, oxygen goes evenly spaced around. Why is nitrogen in the center? Because it's the first one. Join them up, but never in a triangle. That's higher level. So I've got 3 electron pairs, and I have 12 to distribute. So I have 9 more to put in around the molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that every atom follows the octet rule. So what shape is that? Well, it's trigonal planar. So how is it trigonal planar? The central atom has 3 electron domains. An electron domain is a single, a double, a triple, or a lone pair. So for this nitrogen, this electron domain, that electron domain, and that electron domain, they're going to try and get as far away from each other as possible. Like the 3 annoying kids in my class, I try to sit them as far away from each other as possible at the points of an equilateral triangle. So trigonal planar, and that's going to be 120 degrees. What about this double bond here? Doesn't that cause it to be different than 120? It's not really a double bond, is it? It's actually a 1 1/3 bond. So resonance structures are possible with nitrate. So that's going to be 11B, correct. 12. Propanone. So propanone, if you draw it out trying to show the shape, looks like this. Oh, that's a bit funky. Let's put the H3 over here. So it's actually a polar molecule. The molecule has a dipole. The top of this molecule, that's backwards. Come on, Thornley. No, it isn't. That was completely right. The top of the molecule is a little bit negative. Oxygen has a high electronegativity, loves electrons, which means the bottom of the molecule is going to be a little bit positive. How do I know that oxygen has a high electronegativity? Well, because looking at the periodic table, fluorine has the highest electronegativity and oxygen's right next to it. So oxygen's going to really love electrons too in a pair, in a bond. Is this banging on there? No. So if I was to have another propanone molecule, because we're looking at intermolecular forces, forces between molecules, let me just draw that out. And there's another dipole there. You can see that there's going to be some attraction between the negative end of that oxygen and the positive of the hydrogens above. So that's called a dipole-dipole interaction. Dipole-dipole. They're behaving like little magnets. It's like having a north and a south, and a north and a south, and they're attracting. Now they've asked for the strongest intermolecular force because, of course, anywhere there's electrons and protons, you're going to have London dispersion forces. 13. I always get nervous doing this experiment. Here's a glass petrol bomb. Light it up and heat up a beaker of water. Just don't drop the petrol bomb on the ground. Now this is a terrible experiment. It gives like a 40, 50, 60% error, and that's due to heat loss. You think that you're heating the water with the alcohol, but not even half of it goes there, does it? So that's 13B. The others are true in the sense that they cause an error, but they don't cause the biggest error. Small story time with Thornley. So, and I did this in Bangkok about 15 years ago. I asked the kids to insulate the container. I wasn't clear. I thought they were just going to put a lid on it. But one kid wrapped the whole thing in a fuzzy blanket, a fuzzy kind of towel that we used, blankety towel, to insulate it. 2 problems with that. First problem, you're going to set fire to this towel. Second problem, if the towel does stop the transfer of thermal energy, then the water's not going to get hot either, is it? It's an insulator. I got this one wrong. I've got it wrong twice now. Once earlier today when I screwed up the recording by having this banging onto my big shirt. And once when I actually did it. This has a negative discrimination, which means the better you are at chemistry, the worse you did on this question. That's a hard question to write because there's a little trick that I didn't spot. And here's the trick. They're asking, what's the enthalpy of combustion of butane? Enthalpy of combustion of butane is not this top equation. By definition, the enthalpy of combustion of butane is completely combusting 1 mole of butane, not 2. So I'm actually going to change that to 1. So my 13 is now wrong. That has to be 13 over 2. My 8 is wrong. That should be 4. And my 10 is wrong. That should be 5. This is now the correct target equation. I missed that twice. Now this is a brutal Hess's law, but I bet you don't have to do all of it. Well, let's take a look here. I've got 1 butane there, and I have to have the butane on the left. So I need to flip that bottom equation. If you flip the bottom equation, then it's going to be minus Z, which means 14 is A, because that's the only one with minus Z. I feel smart doing it that quickly. Yeah. 3rd time's a charm. Question 15. Which statement is correct? I see exothermic and endothermic. So let's do an exothermic and let's do an endothermic. Exo, endo. And don't forget, exo's hot, 3 letters, endo's cold. These are the reactants and products. These are the reactants and products. This is energy, energy there. At the bottom is stable. Low energy is stable. And at the top is unstable. Is that enough for us? 15a. In an exothermic reaction, the products have more energy than the reactants. Nope, the products have less energy than the reactants. So A is wrong. B, in an exothermic reversible reaction, okay. So the forward activation energy is the height of that first bump. That's the forward one. The reverse activation energy, if I'm going backwards, it's going to be the height of this even bigger bump. So the reverse activation energy is bigger. No, so B's wrong. Over to the endothermic. In an endothermic reaction, the products are more stable than the reactants. No, the products are less stable. They have higher energy. Higher the energy, the less stable something is. So C's wrong. That means it must be D. So 15 is D. Is that right? Yeah, 15D. 16. That looks like it's to do with collision theory. So for a reaction to occur, you need these 3 things to happen. The reactants have to collide in the correct geometry with energy equal to or greater than activation energy. So if I add water to the hydrochloric acid, that's going to dilute the reactant, hydrochloric acid, and there'll be less collisions per unit time. So A is wrong. B, If I decrease the temperature, well, there's two effects of decreasing the temperature, both of which slow down a reaction. There's less collisions per unit time, and there's less energy. So there's less chance of a collision having energy greater than activation energy. So B, don't work. C, increase the volume of hydrochloric acid. That feels tempting, splashing a whole bunch more hydrochloric acid. But you've already got in more than you need. It says excess. So no, splashing another bunch in, probably not. And D, there we go, decrease the size of the zinc particles. So if you've got lumps of zinc or powdered zinc, by increasing the surface area, you allow the hydrochloric acid to get right in and pretty much make intimate contact with almost all of the zinc, as opposed to just the surface of this big lump. So there'll be more collisions per unit time. So the answer is 16D. Always go back to collision theory for those. Question 17. That looks like energy diagrams again. Let's draw an exothermic one. Reactants, products. The activation energy of reaction is not affected by temperature. That's true. The only thing that you know that changes the activation energy is by adding a catalyst. There's another thing you can do, add an inhibitor, that will make it bigger, that's beyond the IB. For activation energy, that's temperature independent. A catalyst reduces the enthalpy change for the reaction. Well, the enthalpy change is this here, delta H. No, catalyst doesn't touch that distance between the reactant and the product energies. How could you change that? You just have to change the reaction. So, a catalyst reduces the enthalpy change of a reaction. That's wrong. Is that enough? One's right, two's wrong. Yeah, that's going to be B. For completeness sake, catalysts provide alternate reaction pathway. Yeah, that's true. So 3 was indeed true. 18, the second most discriminating. Only the smarty pants got this right. How did I know who the smarty pants are? Well, they're doing really well on this test already. A little bit of circular reasoning there for you. Very TOK Thornley. So you'll notice that the second equation, you've doubled all of the coefficients. So that means that K will be raised to the power 2. Simple as that. If you tripled all the coefficients, it would be raised to the power 3. The only other thing we can do, well, we could halve the coefficients, then K would be raised to the half, square root. Or we could flip the reactants and products, and that would invert K. So if I'd have inverted this reaction, the equilibrium constant would then be 1 over K for that flipped reaction. Not too hard, is it? I'm surprised that was the second most difficult. I think because it's new from the previous syllabus, maybe some teachers are forgetting to teach it. What's correct for this reaction? Let me draw it out. So a Bronsted-Lowry acid donates an H+. So let's have a look. What donates an H+? Well, it looks like that this is the Bronsted-Lowry acid. I can see that an H+ has gone over to there because the water turned into H3O+. So the water must have gained that H+. And if the water gained an H+, that must be
Bronsted-Lowry base.
So what have we got? HPO4. So that looks like D, 19D. If it was an equilibrium sign, then there'd be a Bronsted-Lowry acid and a Bronsted-Lowry base on both sides. But in this case, there's no equilibrium. So it's just on one side, the reactant side. 20. This is the most tedious lesson of the entire 2 years, the 5 reactions of acids and bases. So sulfuric acid, you just have to know is H2SO4. You also need to know that's a strong acid. Sodium hydrogen carbonate, well, sodium is a +1 ion, and you need to know that hydrogen carbonate is a -1 ion. So there's going to be 1 sodium for every hydrogen carbonate. Let's just move those closer together. Now the way I do this, not everyone likes this way, is I kind of make a holding answer. I'm going to put a holding answer in there. And what I'm going to do is I'm going to swap the H's in the acid with the metal. And that's going to give me NaSO4 and H2HCO3. Neither of those two exist, so that doesn't seem very useful. No, I think it is. I know that sodium should be Na2SO4, and this H2HCO3, that's just struggling to be water and carbon dioxide. Want to be water and carbon dioxide, anything like that. There are other ways to try and teach this, but that's the way I do it. Now this is unbalanced, but it doesn't have to be balanced. So the answer is C, 20C. 21, when the IB talks about oxidation, almost always it's to do with the oxidation state going up, or reduction is the oxidation state going down. It was about 2 years ago when I actually realized that reduction means the oxidation state goes lower. It's reduced. That didn't occur to me for like 20 years. That's mad. What I'm going to do is I'm going to try and look for the tricks for oxygen. I know that the oxygen, there's 3 possible numbers for oxygen. If it's an element, oxygen's going to be 0. So I can see 0 there. If it's in a compound, it's -2, unless it's with H2O2, then oxygen's -1, and I see an H2O2 there. So that's an exception. And in water, oxygen is -2. So I think that's it. It goes from -1 to -2. That's reduction. Is that what they want? Yes. Ooh. So they're asking about the exception there. 21C. Correct. 22. Second most difficult. I think that means that that's the least people got it right. So electrolysis, well, you've got a container, you've got a battery, a power supply, and you've got a couple of electrodes. And what are we dipping it into? Calcium bromide. Oh, the IB like calcium bromide because the molar mass is 200. So calcium bromide, I've got some calcium 2+ ions, and I've got some bromide- ions. All right then. Now in standard level, electrolysis makes the elements. Higher level, it gets all kind of crazy. But in standard level, it makes the elements. In fact, the first guy that ever did electrolysis, he made a whole bunch of group 1 elements because no one else had ever made them before. He discovered a whole group. So knowing that I'm going to make calcium and bromine because I always make the elements, is that enough? Well, I have to know which way round they go. So let's look at the calcium. The calcium ion is 2+, so that's going to be attracted to the negative electrode by electrostatic attraction. It's actually going to pick up 2 electrons there. So that means the negative electrode is going to make calcium. So that's A, 22A, correct. 23. Balancing in acidic solution. I actually like these. I have to pretend I like everything about chemistry. I do like these. Okay, so the first thing to do is to split it up into 2 obvious halves. That's what I tell the kids. So I've got iron 2+ to iron 3+, and then I've got this kind of manganate-y thing going to Mn2+. Now I'm not going to put the waters and the H+ in just yet. So what I'm going to do is I'm going to balance in acidic solution. So I'm going to put the waters in first, then I'm going to put the hydrogen ions, and then I'm going to balance out the electrons. Then combine the half equations. So the first one, I can see I just need to add an electron there. Now that's a balanced first equation. The charge is +2 on both sides. For the bottom one, well, I'm going to add water first. I'm going to add 4 waters. Now I've fixed that oxygen. But now I've got 8 hydrogens where I don't expect it, okay? So next up, I'm going to look at the H plus ions. So I'm going to add 8 H plus ions. Nice. Now, how many electrons do I need? Well, the first thing to know is the electrons are going to be on the opposite side on each of the 2 half equations. So I know the electrons have to be on the left. So how many electrons? I think that's going to be 5 electrons. Is that 5 electrons? Yeah, so now each side is plus 2. We're still not done. Now you've got to combine those 2 half equations, but you're not allowed to do that unless the electrons are the same. So I'm going to multiply the top equation by 5, 5, 5. Now I've got the same number of electrons. Now I'm not actually going to take the time to combine them. I think from there I can see what my coefficients are going to be. So this would be 5. That would be 1. That would be 8. That would be 5. That would be 1, and that would be 4. So D is 4. And C is 5. So I think that's D, 23D. Yep, that took me way more than a minute and a half. That's okay. The next one. C4H10O. I don't like this question because I don't think you need to name ethers, and number 1 is an ether, methoxypropane. So I'm going to put a pin in that and go straight to number 2. Number 2 is 2-methylpropan-2-ol. So prop is 3 carbons, and on the second carbon there's a methyl and an alcohol. Put in the hydrogens. Well, I'm just going to cheat a bit. So I've got 4 carbons, 1 oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogens. Okay. So 2's definitely correct. Is that enough if I know 2's correct? No. Okay, the next one is butanal. So but is going to be 4 carbons. 1, 2, 3. And the aldehyde group is that. Let's fill in the others. Every carbon must have 4 bonds. So that's C4, 1, 2, 3, 4, 5, 6, 7, 8. H8, no, that's wrong. So 3's right, 2's right, 3's wrong. So it has to be A, 24A. Nice. 25, hex-3-ene and steam. Well, you need to know 5 reactions for the alkenes, all addition, adding stuff on, not swapping, that's substitution, adding. You need to know hydrogenation, halogenation, hydrogen halogenation, hydration, and polymerization. Well, this one's hydration. Water is steam. So let's draw out hex-3-ene. 1, 2, 3, 4, 5, 6. Hex-3-ene. I'm not going to draw the hydrogens in because it's multiple choice. Just put the bonds. And now the trick is when you add whatever you're adding, in this case it's going to be water, split it in half and stick 1 on here and 1 on there over the double bond. So let me do that. I'm going to break this double bond and I'm going to put half the water there and half the water there. So what's the name of that? Well, that's hexanol, we know that much, but what number? 1, 2, 3. So hexan-3-ol. So that's 25C. Isn't it 4-ol? 1, 2, 3, 4? No. You've got to count from the end that gives you the lowest numbers. So that's going to be 25C. 26. Ultraviolet light. Well, the only reason you need to know about ultraviolet light is that it can break up the ozone molecule. Nothing to do with ozone there. And high energy ultraviolet light can break up the oxygen molecule. No, nothing there. The only other time we mentioned ultraviolet light was initiation, propagation, termination. It was when you're adding, when you're reacting a halogen with an alkane. Your teacher probably did a chlorine with methane. And if you remember, the free radical was in the initiation step. Chlorine gets hit by ultraviolet, breaks the bond, and makes 2 chlorine radicals. So what's the halogen in an alkane? D. D is the only one with a halogen and an alkane. 26, D. 27, acidified potassium dichromate, my first explosion. Man, that was scary. So I've got propan-1-ol. So 1 propanol goes to propanal, goes to propanoic acid. You're probably more familiar with ethanol, ethanal, ethanoic acid. You drink ethanol, it metabolizes into ethanal, you get a hangover and your wee smells. And then your body metabolizes that into ethanoic acid, which sounds dangerous, but it isn't. Vinegar. So I just have to look for propanal and propanoic acid. Well, propanal is number 1, and propanoic acid is number 2. So it's 1 and 2. So that's A, 27A. 28, Q. Q equals mc delta T. They're not messing me with any units. It doesn't really matter, does it? Well, the answer is 6.3 or something, isn't it? So I see that I've got 4 sig figs here. I've got 3 sig figs here. And I've got 2 sig figs here. And the rule is when you multiply numbers, your answer has to have the sig figs the same as that with the least sig figs in the question. So I need 2 sig figs, which is 6.3, so 28 is B. 29, index of hydrogen deficiency. Ignore the equations in the textbooks. That's just awful. So every time there's a ring, you add 1 to the index of hydrogen deficiency. Every time there's a double bond between carbons, you add 1. There's a triple bond, you add 2. What is the index of hydrogen deficiency? Well, how many hydrogen molecules could you jam on if you so chose? Well, so what have we got? I've got a ring and a double bond, so I think that's 2, or plus 2. So C, 29C, piece of cake, and 30. This isn't that hard at all, this paper. Some of them are real pigs, this one's fine. Pentanthreol. So 1, 2, 3, 4, 5 for pentane, and on the 3rd carbon, I've got that. Oh, that was hexanthreol above, wasn't it? Let me draw in the hydrogens. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so how many hydrogen environments? Well, these 3 hydrogens are in exactly the same environment as those 3 hydrogens. So I'm going to have a peak with an area of 6. Then these 2 hydrogens are in exactly the same environment as those 2 hydrogens. So I'm going to have a peak with an area of 4. This one's unique, so a peak of 1, and that one's unique with a peak of 1. So I think it's going to be 6411. A, 30A. That was easy. We're done.